3 servers. 1 crashes. Do the other 2 agree on what data is correct? This is the consensus problem, and Raft is the algorithm that makes distributed systems actually work. Today, we're going to break down exactly how Raft achieves consensus, step by step. Let's start with the fundamental problem. In a distributed system, you have multiple servers storing copies of the same data. This redundancy protects against failures. If one server goes down, others can still serve requests. But here's the catch. How do all these servers agree on the current state of the data? Without a consensus algorithm, you get split-brain scenarios where different servers believe different things are true. You get data loss when a server crashes mid-update. You get inconsistent reads where clients see different values depending on which server they ask. The consensus problem is essentially this. How do we get a group of unreliable machines to reliably agree on a sequence of values? So why was Raft created? Before Raft, the dominant consensus algorithm was Paxos, invented by Leslie Lamport in 1989. Paxos is provably correct and theoretically elegant, but it has a major problem. It's incredibly difficult to understand and even harder to implement correctly. In a famous survey, researchers found that most developers who claimed to implement Paxos actually implemented something subtly different. Diego Ongaro and John Oosterhout designed Raft in 2014 specifically for understandability. Their key insight was that an algorithm people can understand is an algorithm people can implement correctly. Raft decomposes consensus into 3 relatively independent subproblems: leader election, log replication, and safety. Raft assigns one of 3 roles to every server in the cluster. First is the leader. There is exactly one leader at any time, and it handles all client requests and coordinates replication. Second are the followers. They are passive, simply responding to requests from the leader. They don't initiate anything on their own. Third is the candidate. This is a temporary role a follower assumes when it wants to become the new leader. Think of it like a company. One CEO makes decisions, employees follow those decisions, and occasionally someone campaigns to become the new CEO. Now let's talk about how leader election works. Raft divides time into terms, which are numbered with consecutive integers. Each term begins with an election. When a follower doesn't hear from the leader for a random timeout period, typically between 150 and 300 milliseconds, it assumes the leader has failed. It increments its current term number, transitions to the candidate state, and votes for itself. Then it sends vote request messages to all other servers. Each server votes for at most 1 candidate per term on a first-come, first-served basis. If a candidate receives votes from a majority of servers, it becomes the new leader. The randomized timeout is crucial here. It ensures that in most cases, only one server times out first and wins the election before others even start campaigning. What happens when the leader actually dies? Let's say we have a 5-node cluster and the leader suddenly crashes. The remaining followers wait for their election timeouts to expire. Because timeouts are randomized, one follower will typically time out first. It becomes a candidate, starts a new term, and requests votes. The other 3 followers haven't heard from the old leader either, so they grant their votes. With 3 votes including its own, a majority of 5, the candidate becomes the new leader. The entire process takes just a few hundred milliseconds. The old leader, if it recovers later, will see the higher term number and automatically step down to follower. This is how Raft handles failures gracefully. Once a leader is elected, it begins log replication. Every client request is appended to the leader's log as a new entry. The leader then sends append entries messages to all followers, containing the new log entries. Each follower appends the entries to its own log and acknowledges back to the leader. Once the leader receives acknowledgements from a majority of servers, it considers the entry committed and applies it to its state machine. The leader then notifies followers that the entry is committed so they can apply it too. This majority-based approach means the system can tolerate failures. In a 5-node cluster, we only need 3 acknowledgements to commit, so 2 servers can be down and the system still makes progress. Raft provides critical safety guarantees that ensure committed entries are never lost. The first guarantee is the election restriction. A candidate cannot win an election unless its log is at least as up-to-date as the majority of servers. When voting, a server checks whether the candidate's last log entry has a higher term or the same term with a longer log. This ensures the new leader always has all committed entries. The second guarantee is log matching. If 2 logs contain an entry with the same index and term, then all preceding entries are also identical. The leader enforces this by including the previous log entries index and term in append entries messages, and followers reject entries that don't match. How does Raft prevent split brain? The answer is beautifully simple: the majority quorum. Since a leader needs votes from a majority to be elected, and there's only one majority possible in any group, there can only be one leader per term. If a network partition occurs, the partition with the majority of nodes can still elect a leader and make progress. The minority partition cannot elect a leader because it can never achieve a majority vote. When the partition heals, the nodes in the minority partition will see the higher term and sync up with the true leader. No conflicting decisions are ever made because only the majority side can commit entries. Raft is used everywhere in production systems today. ECT, the key value store that powers Kubernetes, uses Raft to replicate its data across nodes. Every piece of cluster state in Kubernetes ultimately depends on Raft consensus. CockroachDB uses Raft to replicate data within each range of its distributed SQL database. TiKV, the storage layer for TDB, relies on Raft for its distributed transactions. HashiCorp's Consul uses Raft for service discovery and configuration. Even RabbitMQ adopted Raft for its Quorum queues feature. When you interact with any Kubernetes cluster, you're indirectly relying on Raft working correctly. Let's briefly compare Raft with other consensus approaches. Paxos is equivalent to Raft in terms of fault tolerance and performance, but significantly harder to understand and implement. Use Raft when you need a crash fault tolerance system and want something your team can reason about. PBFT, Practical Byzantine Fault Tolerance, handles a different threat model where nodes can be malicious, not just crash. It requires 3F+1 nodes to tolerate F Byzantine faults, compared to Raft's 2F+1 for crash faults. Use PBFT or its variants when you're building blockchain-style systems where participants might actively try to cheat. Let's wrap up with the core insight. Raft achieves consensus through three mechanisms working together. Leader election ensures exactly one coordinator at any time. Log replication ensures all servers apply the same commands in the same order. And safety guarantees ensure that once a decision is made, it's never reversed. Together, these give you a system that can survive server crashes, network delays, and partitions, while still appearing to clients as a single, reliable machine. That's the power of consensus. If you want to go deeper, check out the original Raft paper by Ongaro and Oosterhout. It's one of the most readable papers in distributed systems. And let me know in the comments if you'd like a video on how ECT specifically implements Raft inside Kubernetes.